today, we are all happy to have you, Professor Ullman, and please.
Okay. Well, thank you very much, and thank you for coming. I hope to entertain you for, I guess, the remainder of the hour. And this is sort of the menu up here. I want to start by talking about an operation called the relational join. I assume most people know about the relational model. If not, I'll explain it. We'll then talk about how to join relations in parallel. It's important because the join is a very expensive operation. I'll then introduce Mapreduce, which is an easy way to get parallelism. Again, I assume most people have heard of Mapreduce, but I'll explain it. And then to really make it a little more complicated, I'm going to talk about joining three relations at the same time, and finally talk about a very interesting trick for estimating the sizes of sets without actually computing those sets. At any rate, let me plug a book that I wrote with two of my colleagues. It's called Mining of Massive Data Sets. You can download it for free. It's also published by Cambridge Press. And of course, a lot of what I say is in those books. In that book, sorry. Okay, so the relational model. Okay, a relation is nothing more than a two-dimensional table. Got rows and columns, and the columns have names, which we sometimes call attributes. And you're going to join two relations by finding rows or tuples, one from each relation, such that they agree on whatever attributes have the same name in the two relations. So let me show you an example. Okay, here are two relations. First one has attributes city and country, and it tells you certain cities and the countries that they're located in. You can see that. The second one relates countries to continents. Most countries are in exactly one continent. Turkey is odd in that it's actually in two different continents. There's at least one other example. I'll let you figure out what it is. But to join these, well, here's the answer. First of all, the join has a column for every name that appears in one or both of the relations, and it's going to have a row for every pair of rows, one from here, one from there, that agree on the country. So, for example, here, this row agrees on country with this row. It also agrees with this row, but it doesn't agree with that row. When you put these two rows together, one from each relation, you get that row. Okay. So this is the full, you can see the full join there. There are six rows corresponding to the 6 combinations of relations, well, one from, of rows, rather, sorry. One, one from here, one from there. In 6 ways they can stick together. Okay, now I want to talk about a bigger relation, so big I can't show it to you. So as it says, there are about 2 billion, 2.3 billion Facebook users. Let's call it 2 billion. The average Facebook user has about 300 friends. So we can think of the friends relation as if it were a graph. Okay? The nodes of the graph are the people, and there's an edge between two nodes if they are Facebook friends. Okay. We can also represent the same information as a relation that has two columns. We'll call it person 1 and person 2. And for every pair of Facebook friends, you've got a row in which, well, one is person 1, the other is person 2. So there actually will be two rows representing the same pair of friends, depending upon which is person 1 and which is person 2. Okay, so here's a picture, very little graph, as if Facebook only had 4 users instead of 2 billion. This is what it might look like. So you can see, for example, A and C are friends. D is friends with B, but not with A or C. And here's the relation that represents this. That is, A is friends with B and C, so that explains the first 2 rows. B is friends with everybody else, A, C, and D, so that's these 3 rows. C is friends with A and B, and that's these. And then D is friends with only B, so that's that. Okay, so again, this is a little example. We're going to use the little example. But in reality, the graph has about 2 billion nodes and about 300 billion edges. And the relation has twice that, or 600 billion rows. Big relation. Okay. Now, one thing we might want to do is find friends of friends. That is, in the graph, you want to ask yourself, well, you want to find the paths of length 2. That is where A is a friend of B, and B is a friend of C. Okay. Well, you can write this as a relational join. You're going to use the same set of rows, but you have to name the columns properly so that you can join them. It makes sense when you join them. So here's what it looks like. Again, so here's our little graph. These are the same relation that I showed you before. But now the first one I've left is person 1, person 2. But the second one, it's the same relation, but I'm calling the columns person 2 and person 3. Okay. Now, here's the join of these relations. It has actually 18 rows. For example, A and B are friends, and B and C are friends, so there's a row A, B, C in the answer. Okay. Now, what we actually want as our result, we want to get rid of person 2. We just want to look at the first and third columns. So what's important here is that A is a friend of C, and vice versa. C is a friend of A. I should warn you that some of these rows have the same person 1 and person 3. So for example, there's A, B, A. That says there's a path of length 2 from A to B and then back to A. But there's also another path of length 2 where A goes to C and then back to A. So you won't get a full 18 pairs of friends of friends. You'll get a smaller number. Okay. Okay. So when I take the join, okay, and there are really 2 questions you have to ask yourself. One is, when I do the join, how many rows do I get? But then when I eliminate that middle column, some of the rows become the same because they have the same beginning and end. And that I can't tell you how many get eliminated, except it is very common that if two people are friends of friends, there are a number of different people in the middle that could be the middle friend. But one thing we do know is, again, the friends relation has 6 times 10 to the 11th, I think 600 billion rows. And again, the average person has 300 friends, so when you join the friends with itself, you're going to get 300 times this, which is about 1.8 times 10 to the 14th. What is that? 180 trillion, something like that. Big number. Okay. Well, it can be even worse than that because while most people aren't friends of friends, if I want to take the join of two relations in the obvious way, I have to do a double loop. Okay, I say for each row of the first relation, I have to look at every row of the second relation to see if they share a common attribute. So that would take, of course, 6 times 10 to the 11th, the number of rows, squared. To do that, that's this huge number. I think it's about half of Avogadro's number. It's just unimaginably large. You can't possibly do it this way. Okay. Fortunately, you don't have to. Okay. Because there are two things. First of all, you can use parallelism. The join is a very easily parallelizable operation, but also you have to be very clever in order to focus on the pairs of rows that do join without looking at every pair of rows. Okay, so let's talk in general. If I have two relations, one, let's say columns x and y, and that's going to join with another relation with columns y and z. I'm going to take a hash function that hashes the y value. And each row from whichever relation is going to wind up in a bucket depending on the hash value of y. Okay. And you can then you can then, if you have one processor for each bucket, they can all the processors can work in parallel on their bucket. Okay, so what that says is, if I have 100 processors, I can hash to 100 buckets and get 100 times speed up. Okay, and the nice thing about this process is, in order for an xy row to join with a yz row, they have to have the same y value, obviously. And if they have the same y value, since you're throwing things into buckets based on the y value, you know they'll wind up at the same bucket, and therefore they will be processed together. And so we will find every pair of rows, one from each relation, that join. And you don't have to look at every possible pair of rows. Okay. So I'm going to give you a little example. Suppose we'll have two buckets, two processors. And let's just say arbitrarily that when my hash function hashes A and B to one bucket and hashes C and D to the other bucket. So what things look like is this. So here is the first bucket. Notice it gets all the rows from both relations that have either A or B as person 2. And the second one gets all the rows where person 2 is C or D. And now I can work in parallel on this set of rows, this little smaller relation, and smaller relations, and in parallel I'll work on these two smaller relations. And I know I'm not going to miss anything because, let's say, a row from here can't possibly join with a row from here because they've got to disagree on person 2. Okay, here it's either A or B, and here it's got to be C or D. So what do you get? Well, most of the rows of the answer come out from the first bucket. You get these 5 rows from the second bucket. Okay, and the important thing is you get all the rows that you would have gotten if you'd compared every pair of rows, one from each of the relations. Okay, so now let's turn to Mapreduce. It's a very, if you've never seen it, it's a very interesting idea. Basically, it's a programming system. It's implemented first. There was a Google program called Mapreduce that became the open source Hadoop program. Now everybody's sort of using Spark, but same idea. And what it lets you do is you can get a lot of parallelism without having to think about parallelism. You write only serial code. Now, it doesn't work, by the way, for anything. It won't parallelize anything, any imaginable thing. But it's very good for many of the common parallelizable operations that you can do. And join is a good example. Okay, so as I said, as I should have said, okay, again, you write 2 pieces of code called a map function and a reduce function. A system like Hadoop then will take your code and apply your functions in parallel, and then it does some hidden work, which I'll tell you about. First, there's a map stage, then the hidden work, and then the reduce stage. And again, the great thing about this is you just write 2 typically simple small functions, and they're serial functions, and then all the parallelism is done for you. Okay, so a MapReduce system, then, the first thing it's going to do in parallel, it will apply the map function that you wrote to every input. And it can do that in parallel using as many processors as are available. Now, as I said, you can't just write any functions as map and reduce. There's a constraint. You have to write a map function that produces a set of key value pairs. In other words, the output of the map function has to have a particular form. Okay, so let's see how you'd write a map function to join, let's say, the person 1, person 2 relation with a person 2, person 3 relation. Well, okay, first of all, a map function can produce any number of key value pairs for one input. In this case, it will only produce 1 key value pair for each row of the input. And whichever relation the row comes from, it's going to produce 1 key value pair where the key is person 2. That is, if it comes from the person 1, person 2 relation, then it's taking the second column. If it comes from person 2, person 3, then it's taking the first column. But the key is always person 2. And that's good because these, what that means is if two rows, one from each relation, could join, then they will have the same key. That turns out to be very important. Okay. Now the value associated with that key has two components. Call them I and X. I just tells you, did this row come from the first relation, that is person 1 or person 2, and person 1, person 2, or from the second relation, that is person 2, person 3. And then the value of X will be the other part, the part that's not the key of that row. So if it comes from the first relation, the value of X is the person 1 value. If it comes from the second relation, then it's the person 3 value. Okay. Now, behind the scenes, what's going to happen? Okay. The system groups all the key value pairs that all the applications of the map function have generated. Okay. And it groups them according to the key. And it assembles for each key a pair consisting of that key and the list of all the values that are associated with that key that it has found. And then these key list of values pairs become the input to the reduce stage, which means you have to write a reduce function that can handle that. So here's an example again. This is the relation that we're joining with itself. For key A, well, if this is the first copy, that is person 1, person 2, then there's this row that has key A, and that row has key A. So you're going to, you'll produce a pair, let's say, from this, you'll produce a pair that the value will be 1, so it comes from the first relation, and then the other attribute will be B, so you get a 1B pair. The second copy, again, these two rows will have key A. And so what you get for your reduce function will be this. The key is A, and then there's 1B and 1C that says there's a B associated with A and a C associated with A in the first copy of the relation. And then similarly, a 2B and 2C because B and C are also associated with A in the second relation. Okay. Now, you apply, again, the reduce function to these key list of value pairs, and the output of what's called the Mapreduce job is the union of what your reduce function produces from every key and its list of values. I like to call the application of the reduce function to a key list of values is a reducer. And so in our example, let's see, we're going to take we'll take each value of the form 1x on this list for the key. Let's say if y is the key, we'll find all the 1x's and all the 2z's, and from each combination of a 1x and a 2z, we'll produce an output row that's got x for the first column, y, that's the key in the middle, and then z in the third column. So this could produce the square of the number. If you have a list of length n, you could get as many as n squared over 4 rows. Okay. Now, one of the nice things is that everything on the list with a 1 joins with everything on the list with a 2. So you're only looking at really as many pairs as you have to look at. Okay, because every time you look at a pair, it actually does join. Okay, so this is the minimum amount of work you can possibly do. Well, it might be probably not too important, but usually the number of reducers is very large, so you're going to group them into reduced tasks. You just don't have, let's say in our example for Facebook, you'd actually have to have 2 billion processors. Nobody's got 2 billion processors. So you group many reducers into a single reduced task. The reduced task, each reducer is executed serially, but you get as much parallelism as you can get from how many processors you've bought. Okay. Now, if that's not enough, I want to talk about an even harder problem. Instead of friends of friends, now I want to find friends of friends of friends. Okay. So that's the same as finding the paths of length 3 in the friends graph. Okay, so now we've got even more work to do. Again, this is just a little more arithmetic. You've got these 2 billion nodes. Each node has 300 friends. That node has 300 friends, and then each of those nodes has 300 friends. So you get 2 times 10 to the 9th times 300 cubed. That's this number. I don't even know what the name, how to say that number, but it's big. But let's look at it this way. In the most compact way to represent friends, each friend is a 32-bit integer. Right? There are 4 billion such integers, so you got enough to cover all the Facebook friends in 4 bits. So a row is only 8 bytes long. Okay. Even in that case, you multiply, 5 and 4 times 10 to the 16th by 8 bytes, you get about 400 petabytes. So that, okay, this is the size of the relation we're going to try to construct. Now, again, the actual output would be less than that. I can't say how much less, but you would expect if 2 people are friends of friends of friends, that there are lots of different ways they're connected. So it's going to be, the output wouldn't be as big as 400 petabytes, but still too big to construct. And at any rate, before you can eliminate duplicates, you have to see all those paths to see what paths have the same ending points. Okay, so the obvious way to do this is as two-way joins. You start with joining 2 copies of friends, call it person 1, person 2, and person 2, person 3. And then you can project out the person 2 from the result so that you eliminate the duplicates. And now you have a relation person 1, person 3. That's the one we really computed just, we've been talking about all this time. Okay, so person 1, person 3, these are friends of friends. And then you join the friends of friends with another copy of friends. So that gives you the friends of friends of friends. Person 3 is now the joining column. And then you project person 3 out of the answer. And that gives you all the person 1, person 4 pairs that are friends of friends of friends. Okay, well, again, just to look at the sizes, again, assuming that a row is only 8 bytes long, just joining friends with itself gets you over a petabyte, and then you eliminate duplicates, so it'll be somewhat smaller than a petabyte, but still bigger than the friends relation itself. And then in the next step, you join that bigger relation With friends, again, you get something that's much larger than 1.5 petabytes. So I really don't want to do that. Okay. So what I'm going to do is I'm going to, when you're faced with something you don't really want to do is you pretend that you really wanted something else. Okay, so, do I really need to know all of these paths of length 3? I claim that there's a good motivation for just asking for each person. I want to know how many friends of friends of friends do they have. Okay, the application might be to find what are called influencers, people who have a lot of connections, so that if they, let's say something is good, a lot of people will eventually learn that this thing is good. So that they're called influencers. And so we don't care exactly who your friends of friends of friends are. Just want to know that you have a lot of them. Okay. So we're just going to count them. But in principle, even to get a count of how many friends of friends of friends you have, the obvious way to do this is to compute all the paths of length 3 and then count how many people are at the end. You're at one end of this path of length 3. How many people could be at the other end of the path of length 3? So I want to show you two things we want to do. First of all, we're not going to count exactly. We want an approximate count. Okay. I mean, if you want to find the influences, you want to find people who have big counts, you probably don't care exactly what that count is. And the second thing I want to tell you about is joining 3 copies of the friends relation in one round of Mapreduce. That is, there'll be only one map function, one reduce function. This avoids constructing the intermediate relation, which is rather big. Okay. So here's the setup. We have 3 copies of friends. I'll call it person 1, person 2, then person 2, person 3, and finally person 3, person 4. And I want to join all 3 of them together in a single Mapreduce job. As I said, it's going to avoid constructing that intermediate relation, but there's a cost to this. Well, we don't construct the intermediate relation. What we do is we have the map function is going to send rows. From each row, it's going to compute many key value pairs, not just one key value pair, as we did when we were just joining one relation with another. Okay. And as a result, this increases the communication between the map stage and the reduce stage. And so we don't want that communication to be too large. So here's how we're going to do the 3-way join. We're going to first of all pick some hash function that will hash people to a number of buckets. I'll call it B buckets. And we're going to hash both person 2 and person 3 two buckets using the same hash function H. And the bigger I make B, the less work there is to do, but the trouble is I'm going to need at least B squared processors working in parallel if this is going to make sense. So that sort of limits B. B can't be bigger than the square root of the number of processors. Now, the keys, or equivalently the reducers, will correspond to pairs of bucket numbers, say I and J, where I is the bucket for person 2 and J is the bucket for person 3. So here's a picture that might help you. Here I'm using b equals 4, very small choice of b, but the row will correspond to the hash value of person 2, and the column to the hash value of person 3. So for example, this key, the key 2, 1, or the bucket for 2, 1, will correspond to, what I'm going to do there is I'm going to join 3 rows, one from person 1, person 2, that has person 2 hashing to 2, and I'll join that with person 2, person 3, where person 3 hashes to 1, because that's the column, and then also I will join that with what you're going to find here for this reducer will be any row from the third relation that has person 3 hashing to 1. Okay. Okay, so here's how the map function is going to work. Okay, so suppose I have a row, say PQ, from the first copy of the relation. That's person 1, person 2. Well, Q tells me what person 2 is. So if I hash Q, I know what the first component of the key is. It's H of Q. That's going to be, let's say, 0, 1, 2, or 3. But I can't see person 3. So I don't know what the hash value of person 3 is going to be. So I have to cover every possible value. So I'm going X can be any of the B buckets for person 3. So as I said, so now you're generating B different keys from one row of the person 1, person 2 relation. Person 2, person 3 is a little bit better because now I know I see person 2 and person 3, so I just I can hash P to get H of P, and I know exactly what the bucket for person 2 is. I hash Q, and I know that the bucket for person 3 is H of Q. So those rows only go to one bucket. And then for person 3, person 4, you got the sort of the similar problem that you had in the first case, where P tells you what person 3 is, so you know that the person 3 value will be H of P. That's just one value, but you don't know what person 2 is, so you have to cover all possibilities by letting Y be any of the B possible values. So again, let's assume that H of Q is 2 and H of R is 1. So if I have P, a row PQ from person 1, person 2, that goes to the whole row with I equals 2, because you don't know what J is. You know that I is 2, but you don't know what J is. If you have, say, QR from person 2, person 3, you know exactly where that goes because you can hash, you know, a hash of Q is 2 and hash of R is 1. And then let's say R and S, the row RS from person 3, person 4, you know that R hashes to 1, so you know the column, but you don't know the row, so it goes to all 4 of these. And then when you look at the 2, 1 key, you know that that the 3 rows that will all join together, PQ, QR, RS, they will all meet at that reducer. And in fact, any 3 rows, one from each relation, that join together will meet at one of the B squared rows. So how many rows have to get, or how many key value pairs have to get sent from the output of the map function to the input to the reduce function. Okay, now let's suppose we're going to have b equals 10. We'll use 100 processors, so get 100 times speed up. Now, for the two end relations, the person 1, person 2, and person 3, person 4, you don't know one of the, either you don't know the row or you don't know the column, so you have to send that same row to 10 different processors. Again, for the middle relation, the person 2, person 3, you know both the row and the column, so you just send it to one processor. So how many rows get communicated? Well, it's 6 times 10 to the 11th. That's the number of rows in the friends relation. 10 for person 1, person 2, 10 for person 3, person 4, and 1 for person 2, person 3. That comes out to this number. It's a very big number, but it's smaller, significantly smaller, in fact, than the number of rows you'd get if you just joined two copies of friends. That is, if you use the naive way of computing friends of friends of friends. So we at least have some hope that this will involve less communication, and less work. And by the way, if you use 100 processors, you would expect that the output will be produced 100 times faster than if you used one processor. Okay, well, if we want to do this even faster, let's throw more processors at it, right? Okay. The trouble is, the more processors you use, the larger B becomes, and therefore the more communication. If you have about 22,000 processors, then the number of rows that you have to communicate from map to reduce is about equal to the size of that intermediate relation. So it's not clear that you could productively use more than 22,000 processors in this example, because that's a lot of processors. But there is a limit. Well, probably worse is, I don't care how you compute friends of friends of friends, the output is very large. And you can't change that. But remember, we said we're not going to compute the friends of friends of friends. We just want to get a count for each person of how many friends of friends they have. Well, again, you have these B-squared processors, and you could count, you could just do the count for every person locally, but you can't then just add the counts, because there will be duplicates. That is, two different processors may discover that you have the same friend of friend of friend. Okay. So it's not clear that you can do these counts and take advantage of the parallelism. Well, so we have to use another way. We're not going to get in. We're not going to do the exact count, as I said. Now, the last thing I want to talk to you about is something called the Flajolet-Martin algorithm, and it has, among other things, it can do. You can estimate a size of the union of sets without constructing the sets themselves, and that's exactly what we want. We never want, we have, let's say these B-squared processors, each producing, contributing to the count of your friends of friends of friends, but you want to be able to take the union of what each processor produces without actually writing down the unions, the sets themselves. Okay, so here's how the Flajolet-Martin works. First, we're going to keep a number of variables. The more variables you keep, again, I'll tell you what a variable is. The more variables you keep, the more accurate your count will be. If you keep 100 variables, that's probably good enough in this application. Now, a variable is a small integer. And by small, I mean really small. 5 bits is enough. And I'm going to assume that a variable is actually 5 bits. Okay, now associated with each variable is a different hash function. And this hash function is going to take a user, in this case, a username, and it's going to hash it to a bit string. And we have to learn a concept called the tail length of a bit string. Okay, it's just the number of consecutive zeros at the end of that string, at the right end of the string. So, for example, the tail length of this bit string is 0 because there are no zeros at the end. Here's another string that has a tail length of 3 because it ends in 3 zeros. Okay. Now, the object of variable v will be to record the largest tail length it ever sees. Okay, that's all it needs to do. Now, suppose that a variable v has recorded r, that is, the longest tail length it's ever seen is r. It's going to estimate that you've seen 2 to the r different values. Okay, why does that make sense? Because if I've seen 2 to the r different values, there's a good chance that I'll see any bit string of length r at the end, and in particular, there's a good chance I'll have seen the bit string of r zeros at the end. Okay, again, it's a little bit more complicated than that, and again, we're trying to again, each of, let's say, these 100 variables gives you another estimate of what of how many different values you've seen. That is, how many different friends of friends of friends do you have? Well, you have to combine it. Taking the average doesn't work. Taking the median doesn't work. So it's a combination of averages and medians. I'm not going to go into that exactly. But so as I said, again, now coming back to this problem of, again, the reduce function is generating triples of rows that join together. We're not going to keep the row itself. All we want to do is to keep track of the maximum tail length for each person. Okay, so if let's say if I find a path of length 3 that goes from person P to person Q, then I use, for each variable, I use its hash function to see what the tail length of person Q is, and if it's bigger than the biggest tail length I've seen so far, then I change that value of that variable to this new larger tail length. And as I said, in this application, at least 5 bits for a variable. That lets you count from 0 to 31. That's really quite enough. Okay. And as I guess I actually said this, whenever the reduce function generates a path P to Q to R to S, then you take each hash function, apply it to S, and you see if it has a bigger tail length, than the current maximum tail length for that hash function and the person P. Okay. Time is about up, which is good because the slides are about up too. Okay, so 100 of these variables at 5 bits per, that's 500 bits, 63 bytes. And so what I need to produce, that is, the reducer is actually going to produce pairs consisting of the person, which is 4 bytes, and the 63 bytes representing the maximum tail length for that person and each of the 100 variables. And so that comes out to something that's really, compared with the numbers we've been talking about, this really isn't that many bytes. It's smaller than the friends relation itself. Okay. Now, again, remember, this is coming out of each reducer. But again, you don't, when you try to combine the results from the reducer, all the reducers, you don't know exactly who the friends of friends of friends of P are. But you do have those variables estimating the number of friends. And the trick is very simple then. You just take the maximum tail length that comes out of each of the processors or each of the reducers, and you use that maximum to help estimate the size, the number of friends of friends of friends of each person. And then you combine the estimates in a way that I didn't tell you. But as I said, it's a little bit tricky, but it works. Okay, so just to sum up, again, joining relations is what's sometimes called embarrassingly parallel operation. You can really get a lot of parallelism in there. Mapreduce is a really good way to write parallel programs without forcing yourself to sort of think about the parallelism itself. One of the interesting things about Mapreduce is that there are cases, such as the friends of friends of friends example that I gave you, where it makes sense to try to join more than 2 relations in one single Mapreduce job rather than doing a sequence of Mapreduce jobs. And then finally, the Flajolet-Martin algorithm is a cool trick that lets you estimate sizes of sets without actually having to see the sets themselves. Okay. So anyway, thank you very much.